let us get started with a motivation to regularization theory, understand the idea behind well posed and ill posed problems and why we need regularization, and in the process how we alter our functional to include the regularization term, and then how we can solve these problems. Okay. Now, a motivation to this starts with machine learning problems we encounter in real life. We have situations where problems are not well posed, but let us try to understand what it means. When the number of data points in the training samples is much larger than the degrees of freedom, the problem is overdetermined, right. So, the motivation to this is, imagine you have a system of linear equations. Let us say we think about solving simultaneous equations in two variables, x plus y equals 5 and x minus y is 3, then you can solve x and y exactly, right. Suppose I give you x plus y equals 5, I have x minus y equals 3, two simple linear equations. I have two variables, two unknowns and two equations, I can solve them, right. But often if we complicate this, we may have fewer number of equations, but a lot of data samples, or fewer number of degrees of freedom in the parameters that we would need to estimate in the functional form of the representation of data, right. So, I have my desired d to be some function of the data point x, d equals f of x, and this function f may have some parameters, and the number of parameters that I need to solve is far fewer than the number of training samples I have, which in case it is an overdetermined system of equations, right, and not necessarily in linear form. Now, what happens because of all this is we may fit misleading variations in the data. This is very important. We may fit misleading variations in the data. So, this is one instance where this problem is not well posed, right. Now, what is our feel for learning? I mean, learning is a very broad qualitative term, right, but in the language of mathematics or machine learning or neural networks, right, we have to think about it as a sort of multidimensional mapping f that can be viewed as a problem of hypersurface reconstruction given a set of sparse points. So, these are important things. I am given the domain x where I have my data points. This can be in a multidimensional space. I have a range. This can be a vector, it can also be a scalar. For example, if I want to have an association or a label to a data point, it can be a scalar, but it can also be a vector in a broad context, right. So, given the domain and the range, so now our data points has these pairs x and y, that is x is the domain and y is the range, and I know these pairs xi and yi, and they are connected by a fixed but unknown mapping. A good example to imagine this is, I take an image of a cat and I extract the feature vectors from this image, and I want to associate these feature vectors to a label of a cat. Maybe the label is 1, maybe a dog label is 2, right. Again I take a dog image, I extract the feature vectors, and then I want to associate a label. So, now the learning problem is basically this mapping f from x to y that forms this association. Okay. So, we assume that x and y are metric spaces, and the problem of reconstructing this multidimensional mapping is now basically viewed as a problem of hypersurface reconstruction problem over a sparse set of points, because if you look at the space in the domain, right, let us say it comprises of R 20, that means we have feature vectors in a 20 dimensional space. Now, I may just get about a million points, but a 20 dimensional space is quite large, right, and we may just get a sparse sampling from those from that space over which we need to do this reconstruction problem. Okay. So, now coming to the problem of reconstruction itself, this problem is well posed if it satisfies the following conditions. So, let me highlight what the conditions are. One is existence. For every input vector x belonging to the domain x, capital X, there exists a vector y which is equal to f of x, where y belongs to y. So, I have to write this as a equality. There exists some y which is equal to f of x, and my vector y belongs to the range capital Y. Uniqueness. For any pair of input vectors x and t belonging to the space capital X, if f of x is f of t, then it implies that x equals t, right. F of x equals f of t if and only if x equals to t, and if this is satisfied, then it is unique. That means, in my range I have these 2 points that are exactly coinciding, and if they have the same values in the range, then in the domain the vectors have to be the same, right. This is a very important property. If the mapping is not unique, then I can be wrong in my association, because I want, if I go from an image of a cat to the label, and then from the label if I were to think about the inverse problem, you know, that it should be in sort be preserved. We do not expect this to be having an inverse mapping, not necessary, but it should be unique. That means, if I give you vectors x and t in the domain, and if they are the same, then the ranges the points in the range have to be the same. Continuity. So, what this means is as follows. For any epsilon greater than 0, there exists a delta which is a function of epsilon, such that if my data points x and t are within a delta ball, right, that is the distance between x and t is less than delta, this implies that the distance between f of x and f of t is within epsilon. So, this can be sort of visualized easily through this diagram here. So, I have points t and x, and I mean, if I position this ball here with center x and radius delta, and a point t is within this ball, therefore, the distance between x and t is less than delta, then with this mapping f, I go to the range space having f of t and f of x, and if I position the center in the range ball with f of x, and I draw a sphere with radius epsilon, then this point f of t lies within this ball. Okay, that is the meaning of the continuity constraint. Now, the uniqueness is very important, because when we look into optimization problems, we want to drive a solution to uniqueness, right. If we bring in 2 or more solutions, then the question is, what is the best solution to pick from this set, which makes this problem ill-posed, right. So, there are 3 conditions: existence, uniqueness and continuity. All 3 are very important criterion for a problem to be well posed, and in particular we pay attention to uniqueness. Okay. Now, how do we make an ill posed problem well posed? For this we need something called regularization, and this theory was proposed by Tikhonov long time back. So, by imposing certain constraints on this mapping depending upon the geometry of the problem, we can make an ill posed problem well posed. Okay. Now, let us see a few details how we can set up this up. So, consider the following problem. We have an input signal that comprises of these points x suffix I belonging to an m naught dimensional space I equals 1 to n, and I have my desired signal associated with this vector xi, and let me call this as d suffix I, and let me assume that this belongs to reals. In general, I can have my desired signal to be a vector as well in some other dimensional space, but I assume it is a scalar here, like the label problem. Now, given these pairs xi and di that constitutes our data, we form the approximating function, or to be this capital F, and therefore we get the approximation error, which is basically the square error between d suffix I and f of xi, right. For every xi I have capital F of xi, and that is what is my response, is what I need to get, and d sub I is my desired, which will drive how f has to be, right, because we are trying to learn this. This is basically my approximation error. So, I have not normalized with a scale factor capital N, but we will ignore this at the moment. Now, we introduce a regularization term that depends on the geometry of the problem. I think it is important to spend a little bit of thought here as to how we bring in constraints. So, now imagine we are interested in a path planning problem, that is, I need to go from part A of the city to part B of the city, and in the process I have to select my path, right. This path can be, I want to minimize my traffic commute time, that means I need to reach faster, but in the process of reducing my commute time I may choose my distance to be large, I may choose a freeway there, right, and if I choose a freeway, then the cost I may be putting on my gas or fuel could be more, right. So, these are all constraints. So, when I start imposing these constraints, I have to regulate over all possible paths that I can choose, I choose a particular path that solves my problem. Another good example is I want to figure out the position of a particle from point A to point B subject to certain constraints that the velocity cannot exceed a certain limit, the acceleration cannot exceed a certain limit. So, based on these constraints I can kind of vary my speed and acceleration, and then I need to figure out the position of the particle, right. So, same thing with neural networks. I give you a set of data points. Would I want to impose constraints on the sparsity in the parameter space of the neural network? That means I want to weed out dead neurons in some way, or do I want to impose some conditions on the synaptic connections, etc. So, these are all constraints that I want to bring in, and they are all regulatory constraints. So, depending upon the geometry of the problem, one can bring in these regularization terms, and typically this functional that depends on the regularization term is given by 1/2 the norm of d times f square, where d is a linear differential operator acting on f, right. This operator can have higher derivatives, it can take d by dx, d square something upon dx square plus d square plus third derivative, fourth derivative, up to some n derivatives, right. Up to some n derivatives I can define this linear differential operator that acts on this functional f, or this approximating function f, right. So, the differential operator acts on this approximating function f up to these constraints, and the choice of the differential operator is problem dependent, because I may restrict myself to the first derivative, I may go with second derivative, so on and so forth, depending upon what I need to bring in as my constraints that should satisfy the geometry of the problem. And the norm here is the norm over which the function space belongs to. Typically we deal with L2 norms, and the geometry of the L2 norm is a circle, right. You must be knowing what these different norms, how these norms look like, right. I can have an L1 norm which is like a rhombus, I can have an L2 norm which is a circle, I can have a soup norm, so on and so forth, right. So, the geometry, so the norm, the choice of the norm depends upon the problem at hand, and that defines sort of the geometry where this function lies, okay. And for more details on this on these norms, you can look into my other course, mathematical methods and techniques for signal processing. I have dealt with the norm spaces etc. in quite detail, and you can further your understanding there. Now, going forward, this functional that we have can be decomposed into two parts. The first part is Es of f, which is basically corresponding to the approximation error, and the second, which is E suffix c of f, is the regulatory term. Okay. And these two functionals, which is Es of f and Ec of f, are coupled by a parameter lambda, and this overall functional E of f is also called the Tikhonov functional. This is terminology. and hence the name Tikhonov regularization, because we are bringing this regularization term here into the functional, and we want to solve this hypersurface reconstruction problem subject to the regulatory conditions. Now, how do we regulate? And this regulation is governed by the parameter lambda, and when lambda equals 0, it is completely unconstrained, and when lambda equals infinity, we do not care about the data points. That means they are unreliable and you are completely driven by the regularization term, right. So, again to mark the differences, when lambda equals 0, it is unconstrained, and when lambda equals infinity, then you do not care about these xi's and you just worry about, because the weight is heavily resting on the regularization term, and that is what you are kind of optimizing. In practice, we choose a lambda between 0 and infinity, and typically you would normalize so that lambda belongs to 0 comma 1, I mean somewhere between 0 and 1. 0 and 1 are extreme parts, right. When 0 is when lambda equals 0, it means it is unconstrained. When lambda equals 1, that means it is only based on the regularization. So, you can basically normalize your functional in a way that lambda is chosen between 0 and 1. Now, getting back to our problem at hand, how do I get my approximating function, which is f lambda of x? That means I need to arrive at this approximating function that minimizes the Tikhonov functional. So, what we are meaning here is we are minimizing the Tikhonov functional over lambda and w. So, lambda is a regulatory parameter, and you may wonder where this w appeared, and w is basically the parameter within this approximating function. So, since you have studied radial basis functions, you can see that you can express the approximating function as a linear combination of your radial basis functions, and choice of those weights are essentially those w's. Similarly, in the context of the backpropagation algorithm also you can bury this w within the as the hidden weights. Okay. Now, what we do is we look at the standard error term differentials in ES and EC by doing a small expansion around the vicinity of that functional, and we would like to see what that means, right. Consider the standard error term, which is ES f comma h, and I look at this differential DES of f comma h. So, what I do is I take a small linear approximation. So, I take f plus beta h, where h is a fixed function of x, and I try to take the derivative and I set beta equal to 0. That is how I compute this differential. Now, and what I want is I want to set this differential of the overall Tikhonov to 0, which means I want so I look at the differential with respect to ES, I look at the differential with respect to EC, and then I want to set that to be equal to 0. I mean, it is what I want from my optimality criterion. But the derivative, but when you optimize this functional, this optimization has to be carried out over lambda and over over the parameter w, right, when I invoke optimality criterion, but here I just consider the small differential and this differential is basically 0, that is what I mean here. Now I expand ES, I take the differential, so it is 1 half d by d beta summation I equals 1 to n d suffix I minus f of x I minus some beta times h of x I. I do the square error here. Now I do this straightforward derivative with respect to beta. So I have a negative sign which sticks out here and the square here and the half cancel out. So I land up with d sub I minus f of x I minus beta times h of x I times the coefficient that scales beta, which is h of x I, and I do the summation for points I equals 1 to n and evaluate this differential at beta equals 0, and this can be viewed as sort of an inner product between h of x and d minus f of x evaluated at the points x equals xi, and that is what this boils down to. Similarly, by doing this differential computation over the regularization term, right, I basically compute d by beta or d by d beta on EC of f plus beta h evaluated at beta equals 0, and this is what I get, which is basically half of d by d beta, this integral d times f plus beta h square integrated over all x in this m naught dimensional space. So doing the simplifications, I land up with taking an inner product between df and dh in this space, right. So in the space H where I can define this inner product, right. Now with this picture in mind, we will now begin our journey with the Euler Lagrange equation, connecting these differentials and then try to see what we can get. Okay. So with this we will end this module and we will work further.